This tutorial will deal with 3D printing, technologies, materials, and applications. I'm Vassili Karanassios. I'm with the University of Waterloo in Waterloo, Ontario, Canada. I'm also a co-founder of a nanotechnology engineering degree program. Several of my students were involved with this research. They're just too numerous to mention. This tutorial is split into two parts. Part one will deal with technologies and materials, and part two will primarily focus on selected applications. There are way too many applications to cover in one tutorial. I'm just going to give you a few examples of the applications that will come in part number two. The question that arises then is, what is the material that will be covered in this tutorial? Briefly, for the last many years, 3D printing has been receiving significant attention in the scientific and the engineering literature. To many, 3D printing is a transformative technology capable of impacting many areas of science, medicine, including medical implants, for example, and dentistry and technology. 3D printing is often described as a tool that has the potential to alter traditional methods of manufacturing. In this tutorial, 3D printing technology will be initially described in some detail. Then, materials used for 3D printing will be discussed, and selected applications will be described. Applications will be drawn from the engineering and the scientific literature and from the author's laboratory. Throughout this tutorial, potential future directions of 3D printing will be outlined, and general comments of societal and economic impact will also be made. The background of the author, it will be briefly outlined next. In 2011, the author and his co-authors from his laboratory, his students, submitted an open access chapter on rapid prototyping dealing with plastic quartz chips for battery-operated microplasmas. Now, this paper, this open access book chapter, has been very well received. It has been downloaded about 2,200 times, and there have been additional papers from my research group. So the author and his laboratory have quite a bit of experience with rapid prototyping and 3D printing. A conceptual outline is provided next. I'll give you a brief introduction. I will describe some of the technology, the materials involved with 3D printing, and applications. Applications, they're too numerous to mention. I will selectively, and it will show my biases, I guess, I will provide on 3D printing of glass, 3D printing of microfluidic channels, bio 3D printing mass spectrometers, 3D printing of microplasmas using millifluidic channels, and at the end, there will be some time for questions and discussion. The question is, what is 3D printing? I will describe this by means of an example. I will start with subtractive manufacturing, where one starts, for example, with a block of aluminum, puts it into a machine, such as a computerized control machine or CNC machine, in which material gets subtracted, and in this case, one is able to build the desired shape. In this case, we have additive manufacturing. And for example, we have an X, Y, Z stage here, and a nozzle that spews out material, the desired material. The material is one layer at a time, is deposited, and in this case, the desired shape is derived. There is an interesting video that I would encourage the attendees to watch at their leisure. In simple terms, we build the model on a computer screen, such as the one shown here. The computer sends in one layer at a time, and you can see it here, one layer at a time, software sliced, if you will, and this goes onto a 3D printer. And the 3D printer can make complex objects, such as the one shown here, or very simple objects, such as the one that we did a few years ago, and I will describe this in some detail later on. One of the questions that usually is asked is, how big is the market when it comes to 3D printing? it will go from 2014 all the way to 2020, and we see it went from $1.8 billion to $3.1 billion, a significant increase in terms of percentages. So the market is relatively big. How big is the interest? In addition to the market, we'll look at the interest, including manufacturability. People talk about 3D printing being the factory of the future, but if we do a basic Google search with the string search 3D printing, we see that we get about 76 million hits. This was done a few days ago this year. More recently now, people can print Inconel, aluminum oxide, aluminum silicate, and pure copper. So people can build a lot of materials that were not possible a few years ago. In addition to printing metals, one can build biomaterials, and this is a nice review, a relatively recent review of 3D bioprinting of tissue and organs in Nature Biotechnology. So in addition to being able to print plastic and aluminum or metals, one can print biomaterials. And I'll make comments a bit later on this issue. A few years ago, a company tried to print a full-size working car for less than $2,000, and we can see the full-size car here, and this was a 3D printing. So in addition to conventional things that people can print, researchers and business people have ventured out and tried to print complicated structures, such as motor vehicles. In addition to printing vehicles, one can print buildings now. There's an apartment building that is built by a Chinese company. It's a 5-story apartment building, and it's very impressive in terms of what 3D printing can do and how rapidly it can accomplish it. Some things we've done in my own laboratory, just using a desktop printer as an example. The desktop printer was less than $1,000. I should add, we built complicated structures, little screws and nuts, and all sorts of things that, as you can see here, and there is a dime here, Canadian dime, just to show, to use it as demonstration for the side. So to look at the 3D printing in terms of its past, its present, and its potential future, I should add, this is an outgrowth 3D printing, that is an outgrowth of rapid prototyping methods, where we started with subtractive manufacturing, as I mentioned before, the traditional way of doing things, then additive manufacturing, and 3D printing really dates back to the mid-1980s. At present, the 3D printing approaches, different materials, different applications, different issues. Bioprinting is something that's coming up strongly, and other scientific applications. I will be making some predictions for the future of 3D printing, and I will provide some concluding remarks, and hopefully there will be time for questions and some discussion. We're going to focus now on selected technologies, approaches, and depending on the material used. Actually, most of the technologies are material dependent. We'll start with 3D printing technology, and initially it was called stereolithography apparatus, or SLA, and digital light processing. This will use the same chips that Texas Instruments has developed that we're using now on our projectors, where we have a laser, and the laser is scanning, generating a scanning beam, and the scanning beam hits liquid resin. There's an XY base and a Z base right here, and where the laser hits, the liquid resin solidifies. I should mention that both stereolithography apparatus and digital light processing are very similar in concept. Fused deposition modeling is another method or another technology where there is a bulk material spool, as shown here, and there's a support material spool, and this is the 3D object to be developed. There's a platform that moves, as a concept diagram in XYZ direction, and the nozzle is heated, so the material, plastic typically, comes out of the nozzle, and when it hits, it solidifies. When it's cooled, it solidifies. Another technology involves selective laser sintering and selective laser melting. Both are used with solid materials, such as nylon and in some cases metal. So there's a laser beam that's coming in, a laser scanner, and the scanner scans in this direction, and when the light comes on, it solidifies the material. The material in this case is powder, and this fabrication piston is moving down, and the material, the powder, is replenished by moving this piston up, and at the end of the this moves in the XYZ direction as before, but at the end one is literally removing the object right from the powder material. There is electron beam melting. It could melt materials, it could reach temperatures up to 1,000 degrees, but it requires a vacuum and is good for metals such as titanium. So there is an electron gun here, there's a wire feed spooler, so it comes in here, and it's an XYZ direction where the material, the substrate is moving, and the electron beam melting, it would melt the material, and when it cools, it solidifies, and it builds the structure, the desired structure. Another method is laminated object manufacturing. It requires some post-processing, such as sanding, may be required. There's a laser as before here. So the laser beam is shown here and is scanning across the surface. There's a heated roller that laminates the material, and where the laser beam is hitting, the material is solidified. This is a simplified concept diagram of laminated object manufacturing. This made the cover of Science, a very well-respected journal called Science, and in this case, there is another laser beam, digital light processing, and wherever the light hits the resin solidifies. So in this case, the Eiffel Tower is literally gets pulled out of the vat full of the resin. I highly recommend that those who take the tutorial visit YouTube and watch this video. Is really very important. This is about 5 years old now, but still very pertinent. The 3D printing materials can be grouped in 4 basic categories: synthetic polymers, metals, ceramics, and glass, of particular interest to chemistry departments and chemistry laboratories. Synthetic polymers, such as nylon, are widely used as 3D printing materials. These are thermoplastic materials, that is, materials that become pliable above some TG temperature, this glass transition temperature, and resolidified once they're brought back to room temperature. An example of that is polyimide polymers, such as nylon 6,6. An example is shown here of the starting material, nylon materials, and some tubes here, different colors, again using nylon materials. A widely used material is synthetic polymers such as ABS, which ABS stands for acrylonitrile butadiene styrene, or ABS. This is monomers are shown right here, and these are mixed in the right proportions to give us ABS. Now, ABS is what Lego parts are made out of. So this is something very familiar and widely used in society. Another widely used material is a synthetic polymer, PEKK, and the chemical structure is shown here. N means this main unit is multiplied many times, and the abbreviation PEKK is for polyether ketone, and is claimed to be an ultra-high performance polymer, can be used as a replacement for aluminum, so a lot of optical mounts can be made. It has really good chemical resistance. It can be used for electrostatic discharge, and because it's safe to electrostatic discharge, and it's widely used for aerostatic aerospace applications. It has low degassing. And here's some materials, some structures that have been made with the PEKK. There's some optical mounts shown here, a gear is shown here, a tube, and even fake teeth. There's synthetic polymers such as resins. They're too numerous to mention here. Some have proprietary formulations. They're covered by high degree of intellectual property. Properties such as color are application dependent. And again, there's a nice video on YouTube that I recommend, and you can see here the light, anywhere the light strikes the resin, the material, the desired material is formed. There's some examples here of different things that researchers or people have made using these types of resins. Materials, 3D printing materials other than polymers abound. Many of them are specialized or require specialized printers, such as high temperature. There are metals and alloys, a variety of them, such as aluminum, titanium, tungsten, tantalum, copper, gold, and silver. Stainless steel alloys, such as Inconel, these were not possible to print just a few years ago, and chrome cobalt alloys. One can also print ceramics and glass. They will have impact on glass blowing, it is my guess here, on chemistry department. And there are other materials such as polypropylene, rubber and rubber-like plastics, silicon-based materials, and graphene to make conductive materials. Proto Labs, and I'm not meaning to single out any particular company that came off the web, a company called Proto Labs. It shows materials that could be printing other than polymers. Here's an example. We're using stereolithography. There's an AND here that's used to provide size. It's a chessboard, for example. Selective laser printer sintering to bring aluminum oxide, and direct metal laser sintering to bring metallic materials as shown here. So one can use a variety of materials, but they would require specialized printers, as I mentioned. Binder jetting is another method of rapid prototyping and 3D printing. This could be used for production. Typically, 3D printing is not used for production runs, but for prototyping. It's one of the simplest methods. It's a print head, typical to that of an inkjet, and it moves in a bed of powder. A binding liquid is deposited at selected locations. The process is repeated until the object has been printed, and the object is removed from the unused powder. The advantages are relatively fast, relatively inexpensive, easy to use color, supports complex geometry. The negative are low resolution, you get rough surfaces, relatively low strength. Functional testing is a question mark because it has been partially tested, and although it's claimed that it can be used for manufacturability, can be manufactured, there are still questions that remain to be. Fused deposition modeling is another method of 3D printing, but it can be used for production runs. The layers are formed by melting and solidifying the resin, and thermoplastic resins include ABS, polycarbonate, ABS blend. It is stronger than binder jet. The advantages are it's widely used, is more expensive than B-jet. The object properties of materials can vary, and it supports complex geometry. The disadvantages are low resolution, one gets rough surfaces, the Z-axis has poor strength, printing is relatively slow, and its ability to be manufactured is still under question. Another method of stereolithography is used for rapid prototyping. A computer control laser is used. A UV curable resin is also being used. The resin solidifies where the laser beam is focused, and the final object emerges really from the liquid resin. The advantages are that reasonably priced, very good surface finish, it supports complex geometries. The disadvantages are relatively low strength. The product may become brittle over time. The relatively slow printing, and of course functional testing and manufacturability, they're still under. Selective laser printing, as a computer controlled laser is used, the layers are fused from powder material. Nylon powder is often the material of choice. Strength is poorer versus what one would get by injection molding or by CNC machining, and may be used as a production method. So the advantages are reasonably priced, supports a range of materials, good accuracy in size and form, functional testing is possible, and it supports complex geometries. The disadvantages is that the surface has a poor roughness, material choice is limited, and manufacturability is still Polyjet or PJet uses a printhead that sprays a polymer resin. The layers are formed and the resin is cured using UV light. The final object is drawn from the pool of resin and has resolution superior to other methods. The advantages are it's reasonably priced, the smooth finished surface that are being provided, and it does support complex geometries. The disadvantages are inexpensive, limited choice of resins, the finished object has poor strength, and manufacturability is still under question. The digital light processing, DLP, uses the same chips that are provided by Texas Instruments that are used on any data projector. It uses also liquid polymer baths, or VATs as they're being called. It is under computer control. The DLP chip directs UV light that cures the resin. The final object is withdrawn from the vat of the type I showed an example that made the cover of Science, but is not suitable for large objects. The advantages are reasonably priced, it's relatively fast, resolution can be high, and it supports complex geometries. The disadvantages are inexpensive, limited choice of resins, medium resolution, that is to say rough surfaces, and manufacturability is still under question. There's a nice video I recommend watching because it's really interesting. Direct metal laser sintering. I want to emphasize the word metal here because one can now print metals. It's similar to selective laser sintering, but for metals and not for plastics. Metals and alloys include aluminum, titanium, cobalt, and the alloys are stainless steel and Inconel. Resolution could be up to 20 micron per layer, which is one of the better resolutions one can see in the Z direction. May be used to make objects that are hard or impossible by CNC machining, and some post-processing, such as sanding, may be required. The advantages are any alloy, at least of the type described here, can be used. It has excellent mechanical properties, the resolution can be high, and it does support complex geometries. The disadvantages are slow vis-a-vis other methods. It can be expensive. Some post-processing is required. High-level expertise required. And manufacturability, it has been tested and proved to be reasonable, if not good. There are a number of resources for materials properties on the web. This will not be discussed, all of them. Will only be mentioned stereolithography. Part 2, dealing with selective laser printing or materials for it, and direct metal laser sintering will not be discussed. It just can be downloaded, as one can see, from this PDF icon. And there are a number of companies that will make both the materials and the printers. This is just an example. I want to emphasize again, there are many resources on the web. If one clicks on the entry that's highlighted in yellow, part of what is downloaded, it will be shown on the next slide for completion. So in this case, the importance of materials selected for manufacturing of the future, so to speak, types of applications, for using stereolithography apparatus, and Acura SL5530. All of the properties are here. I'm not going to read them to you, but there's a great deal of detail there are multiple pages and there are multiple websites that do provide material properties. So I strongly recommend that interested users visit the website and download the materials of interest to them before they start purchasing and printing. Just to provide another example, 3D printing in healthcare, among others, there are many, I should mention, thousands and thousands of them on the web for dental and medical implants, such as hip replacements. The materials used vary. I'm going to go back to 2014. The global market for 3D printing for healthcare had a revenue of about $500 million. The growth estimates are now set at 18% per year until 2020, this year. And the example companies include Digilab, Envisiotech, Invitech, Microfab Technologies, Enscript, Techno Devices, and many, many more. It was very difficult, if not impossible, to cover all of them in this particular presentation. Applications will be discussed next. This is the beginning of part 2. Part 2 will come after the next slide, but select applications will be the focus of the next part. I should mention that the question of how big the market is has been addressed. People looking at growth percent between 2017 and 2024, and one can see an aggregate rate of growth of about, forecasted, of about 29%. This is year 2024. This is the compound annual growth rate, CAGR will be the abbreviation. This is the end of part 1, and then we'll proceed with part 2. This is now part 2 of the tutorial, and it deals with selected examples. As I mentioned before, the examples are too numerous to mention, and it will be impossible for me to cover them all. I'm just going to give you some examples that really reflect my own preferences and biases, if you will. So this then, selected examples will cover 3D printing of glass, 3D printing of microfluidic channels, 3D printing of tissue for tissue engineering, organs on a chip, some selected examples from my own laboratory, examples of 3D printing resources that anybody can access via email from the University of Waterloo, some unusual examples, and uses of 3D printing in education. I will start by using examples of 3D printing of glass. Glass is a difficult material to work with, as any glass blower can attest to, and it's really very important in any chemistry department anywhere in the world. So I will start by discussing 3D printing of glass. 3D printing of glass, and you may ask, why glass? Well, glass is one of the most important high performance materials that are used for scientific research. In industry, they're widely used, and also in society. This is mainly owing to its unmatched optical transparency, outstanding mechanical, chemical, and thermal resistance, as well as electrical, thermal, and sliding properties. MIT begins 3D printing of glass. Glass is a difficult material to work with, even for a glass blower, let alone 3D printing. And MIT started printing a few years ago. This is a description of year 2019 that is an update of what MIT is doing with molten glass, thanks to the MIT researchers. Recently, or relatively recently, in the Journal of Nature, a very well-reputed journal, Kotz and co-workers published a series of papers where they can print glass, as we can see here, and crystal clear also. Here there's 2 Web2 videos that I highly recommend, and overall one can fabricate optical quality surfaces from fused silica. This is very significant for scientific and engineering applications, in particular for lasers, for optics, and spectroscopy. So imagine being able to build optical benches and optical components using a 3D printer, which will reduce cost in a significant way. In terms of fabrication example of glass, as a starting material is a UV curable monomer, an SiO2 powder. Then when the two are mixed together, one ends up with a nanocomposite, is placed through a stereolithography apparatus, and the polymerized composite is shown here, and then debinding takes place at 1300 degrees centigrade. So one ends up with a fused silica glass, which is high quality based on the original paper I read. This is an example. It was done at KIT in Germany. The bar here is shown is about 5 millimeters. So it's not really very big, and it does withstand really high temperatures. This is another example of miniature structures fabricated on glass. The bar here is only 200 micron. For part C, as you can see here, the scale bar is 100 micron, and the insert here is also 100 micron. These are micro lenses micro lenses that can be used for spectroscopy, and this is really very important. I have included a video here that I strongly recommend that interested readers watch it. It does provide a very promising approach, and it has the potential to replace glass blowing in chemistry and revolutionize many aspects of optical spectroscopy. There's some examples here of 3D printed microfluidic channels. This is really important because the field of microfluidics has received very significant attention in the last 20 or so years. If we look here, the scale of things, so to speak, we'll start with a fraction of a nanometer, about 100 picometers, 0.1 nanometers. This will be small scale individual atoms. Then we go to small scale molecules, 1 nanometer range, about 3 to 5 nanometers, it will be the DNA. Now the length of the DNA, it will depend on how many base pairs one is dealing with. It could be as long as about 100 micron or about 200 nanometers. This is where the field of nanofluidics comes in. We have large-scale molecules in the range of 10 nanometers, viruses around 100 nanometers, bacteria in the micrometer scale, white blood cells, 10 micron, human hair, about 100 micron, around 50 to 120 micron, let's just say 100 micron. The tip of a pen, it will be 0.7 millimeters or 700 micron. A 1 cent coin that I will use as an example, it will be about 20 millimeters, and a tennis ball about 7 centimeters. So we have microfluidics in this range, in the micro regime, and then millifluidics for anything that's a bit higher than 1 millimeter. There is a gap here, and this range sometimes is extended, so the microscale can be extended to go from 1 micrometer to about 1,000 micrometer or 1 millimeter. The same with nanoscale, it can be extended from 1 nanometer to about 1,000 nanometer. But the strict definition by this the US is 1 to 100 nanometers for the nanoscale, 1 to 100 micrometers for the microscale, and anything above 1 millimeter for the milliscale. So microfluidics is the study of fluid flow, or whatever it's in the fluid, in the micro or sub-millimeter channels or around microstructures. There are many reasons to use microfluidics: small sample size, lower amount of reagents, thus reducing cost, etc. Implications, significant implications to science and technology. Biology, for example, it does not make enough sample, so we have to use microfluidics. And there are some examples of microfluidic channels that were fabricated using amorphous glass in my own laboratory. There is a 1 cent coin. Remember, that's about 20 millimeters in length. There's a serpentine structure going back and forth in a microfluidic channel. This is the picture is taken as it is, and then this channel was magnified at 100-fold magnification. You can see the meandering structure. This was done for polymerase chain reaction amplification applications, and then it's only when this thing gets enlarged 60 times where we can see that there's a very nice channel around here and very nice corners and very well-defined corners. The question is, can such microfluidic channels be 3D printed? So one will start then as an example. There are many examples in the literature. This is just an arbitrary example. One starts with the computerized edit design. Then this gets converted into a stereolithography file, a file that has an extension file name .stl. Then slicing of the design. You can see the slices here that are being sent to the printer and printed layer by layer. This is an example of layer by layer printing. I'm not going to get into the mechanics of this, but suffice it to say that there's an ultrasonic vibrator that brings in some ink from an ink vessel, and the droplets travel across the deflection electrodes, and the printing takes place in the structure here. There's some examples here, variety of examples. We can see from holes to things that are protruding. The bar here is about 1 millimeter, 1,000 micron. So this thing, it will be about 250 to 300 micron. You can see there's wells here, and you can even see the structure of the well right here is not extremely well defined. Here's another one that shows the side roughness. So we're beginning to see some of the potential issues with 3D printing. And the same thing here, the top is 754 micrometers, but the bottom of this well is 225 micrometers, and the depth is 500 micron, and you can see the structure or the wells, they're not vertical. The walls of the well. This is an interesting example because this is what people would use at the beginning with flasks, so to speak, and then this is what one would get with fused deposition modeling, with polyjet, and with stereolithography apparatus using digital light processing. So these researchers, and I have it here, compared those three methods for the same structure. I should emphasize that the length part here is 500 micron. There's some progress that has been made over the last several years. You can see the structure here doesn't show much, but if you zoom in, this is what you would see. The sides of the walls, they're really well defined. This is 23 micron, this is 13 micron, that's 12.5 micron, and we can see the sides, the side walls are really well defined. So one can get high aspect ratio flow channels. And one can focus on the quality of the channels. You can see here, this channel is really, really nice. This is 500 micron. There's stuck serpentine structures and tubing holes, as you can see here. And this is a microchannel going back and forth, just like the serpentine structure that I showed before. And these are SEM images of the serpentine channel cross section. And one of the things that's important, I have this table here for comparison, because the resolution in XYZ and micron is very, very important. In this case, it's 300 by 300 by 50. In other cases, they're 56 by 56 by 50. The surface roughness is really very critical, and we see here it's about 11. It goes down to 1, and it goes down to 0.3. So it's really very important to look at the surface roughness. The biocompatible materials in some cases are used, and in some cases are not available. And then the reduction factors, the production factors, could be less than an hour, more than a day, or less than 15 minutes. This is really very important for if one is interested in mass producing these channels. Bioprinting is another example that is becoming really important for biochemistry related applications. Bioprinting technologies in hard tissue and organ engineering, they're receiving significant attention. I'm going to jump to the end of the slide in this particular case. When I use a Google search and I use the search string tissue engineering, I get about 9.8 million hits. When I use the search string organ printing, I get about 79,000 hits. And when I do the search string bioinks, I get 148,000 hits. Now, hard tissue, I mentioned on the beginning of the slide, also termed calcified tissue, is tissue which is mineralized and has a firm intercellular matrix. For humans, that will be bone, teeth, enamel, dentin, and cementum. This is for dental applications because covering a whole thing of dentistry. Organs are different tissues working together to perform a particular function. An organ system is a group of organs that work together to do a job. Tissue, a group of similar cells that work together to perform a specific function. For example, brain tissue, muscle tissue, and heart tissue. Organelles, tiny structures which carry out various functions within a cell, and cells are the basic units of any living organisms. I've included here just to refresh and remind you what we're talking about. This is very similar to what we had before. Now we have a plunger that pushes down a bioink or a set of cells. There is a print nozzle where the material gets extruded through the nozzle, and you can see this now is being printed one layer at a time, similar to what we had with conventional 3D printing. Bioprinting of organs, there really are literally many methods. I'm going to give you one generic method as a representative example more than anything else. In this case, organs could be built up a layer by layer. This is an example of cells being printed one layer at a time on top of a glass slide, and then a thermal reversible gel that can be removed, and one can have part of it as an organ being 3D printed. Another conceptual approach more than anything else, there's bioink spheroids that are being printed onto a special biopaper gel. Additional layers are being printed. One can see one on top of the other, and then bioink spheroids fuse together, and as the biopaper now dissolves, and living tissue is being formed, as we can see here in step number 4. So what's really phenomenal here, in my opinion, is that one can start printing now living cells and living organs. So some examples of bioprinting include bioprinting of organs, and we can see we have cartridges now that will print part of a 3D print heart. There is cartridges again that will do in situ bioprinting of skin, and bioprinting of cosmetics that will generate quite a bit of revenue for those interested in generating revenue to advance the cause for 3D printing. There's some resources that are available. This is an example. I found more than 40 books on 3D printing on Amazon. There's one that's called 3D Printing for Dummies, how you would print something. And this is an example of a brain that could be used for teaching purposes. There's a site that says we do teeth, and those interested in might want to visit the website. In Nature, how to print, published how to print blood cells. The Google Scholar, in this case, search with bioprinting gave more than 20,000 hits, and on Scholar, and an example is shown on this link here. Bioprinting via 3D printing received significant attention, for example, using stem cells or tissue engineering. I'm not going to go through this in any detail, but the end result is you can print an ear, for example, in this case showing that you can print a heart, or you can print an organ on a chip. So this tissue models allow researchers to recreate physiological and mechanical functions of the organ, and that's the way, that would be a way to avoid animal testing for drug development and other testing. There's books as well on bioprinting and regenerative medicine. Continuing with bioorgans and 3D printing, Nature used the journal Nature Here's the very catchy title, The Printed Organs Coming to a Body Near You. I've included this because although it's slightly dated, 5 years old, it shows that there has been significant progress over the last years, and there has been significant interest also 5 to 10 years ago in printing, 3D printing of organs. So it's not really very, very new. It's relatively new. So in terms of publications and related 3D printing, 3D bioprinting, number of publications is rising. We see more than 200 publications in 2018. The last year I could find a graph for. So this exponential growth, so it seems, for bioprinting. There is, in terms of what is the market size by technology in 2015 to 2026, about 10-year time span in US dollars, and we can see again an almost exponential growth is being predicted, and the bioprinting market size is expected to be worth about $4.1 billion by the year 2026, with the combined aggregate rate growth of about 20%, 19.5%. So significant financial economic interest as well. I will now show some examples from my own laboratory to show or to demonstrate how we have been involved over the years with 3D. This is an intertwined structure, and this is a miniature version of it. There is a dime here to show size, and we've been playing with this for a long time. Things we have done, we're interested in going from large-scale plasmas to microplasmas, and the idea is to take part of the lab to the sample. So this is an ICP plasma with a spectrometer. If we flip open this door, we see a plasma torch. That's where the plasma is formed. There's a penny here, Canadian penny for size. We want to miniaturize this and go from this to something that's really very small as this. So we have a microplasma formed between two electrodes. You hardly see the electrode here, but there's the electrode here. The microplasma is shown here, and it's called micro because it's formed inside the letter A of a 1 cent coin. This is the actual size, is the size of a sugar cube. So you may ask, what is a plasma? At least as it's used for chemical analysis, not for fabrication, semiconductor fabrication. It's a hot, partially ionized gas, 6 to 10,000 degrees hot. This is what one gets at the surface of the sun. Unlike low pressure plasmas that are used for semiconductor fabrication, these are atmospheric pressure plasmas, and over 95% of the universe is really partially ionized gas, which is a plasma. This is the plasma that's being formed on top of a torch. This is about 20 millimeters in actual size. This coil here is where energy comes in, and this is the sample that's coming in from the bottom. This is the most widely used plasma, about 20 liters per minute of argon, 1 to 2 kilowatt of power, and they're cold plasmas, and I'll talk about it. They're miniaturized plasmas of interest to this tutorial. This is a plasma that's been formed between those two electrodes I showed before. There's a quartz plate here that allows UV light to go through. The sample is coming in from here, and this microplasma in this particular case, which is 3D printed, is a bit smaller than an actual sugar cube. So this is an actual sugar cube of the type one would be inclined to use with their coffee or tea, just to provide a scale. Problem summation, you can see the layer by layer printing, and you can see it here, but it's a rib-like structure. From left to right, we're going 120 micron, 240 micron, 320 micron. And you can see this tube here is not really transparent as we would like it to be because of the ribbed kind of structure. Now, if we take a profilometer, that is a pen, and we try to scratch the surface, and we can see the rib structure shown here. It has some periodicity to it, and it goes from 0 all the way to about 60 micron. and that means that some post-processing may be required depending on the application. So this is an example of the layer by layer structure. You can see it here, and it's just a low resolution print. There is high resolution, and I'll show later on, but you can see the one layer at a time structure of the sugar cube type microplasma. And the same thing here with the profilometer, and you can see one layer at a time, a zoomed in version. This is the scan length in micron, so clearly some post-processing is required. Now, to deal with transparency issues, we purchased an XTC epoxy. So this is the actual 3D printed structure without the epoxy, and then when we use the epoxy here, is more transparent. That's an example of visual test. This is a tube with no epoxy. You can see a battery. Actually, you cannot actually read what the battery is. And when we put the XTC 3D epoxy, we get the transparency back. So there are ways to post-process this thing. And when we use the profilometer, now we're going from minus 20 to about 20 micron, and it's a lot flatter, as you can see. Again, this is the scan length in micrometer. So the rib structure is smooth. A variety of approaches to address transparency. We use a polymaker, polyshare using isopropyl alcohol, and this is one structure that's been 3D printed. It has been smooth, but we lost structural integrity. I'm going to talk about very briefly about the resources available at my university, which is the University of Waterloo in Ontario, Canada. This is really important because nobody can have or can purchase all of the 3D printers that are required for the different materials, and this is a local resource that we can use. Initially, when we started with this, we could send an STL file via email anywhere on the planet, and within days we could receive printed prototypes back at the University of Waterloo. So there are different ways of approaching the resource availability at any place. So in our case, in 2017, we got a multi-million research grant, so that we'll be able to build, as you can see here, and print 3D different structures. Here's another copy of the local newspaper, the second page of the investment that was made for a 3D printing lab, that we have now 8.9 million, and it has now went up all the way to $17 million. So this facility, as I said, can be accessed by email by many people across the world. There's a variety of systems. This is a melting system. There are pictures of it, and you can see some of the structure. So there's a laser in here. There's a student who did the work, and there is the manager of the 3D printing facility at the University of Waterloo. I'm going to briefly mention some unusual examples of 3D printing to show not only progress, but that researchers in the field have been highly creative in developing new approaches to 3D printing. Here's an example of a molecule making machine. So you can program the molecule that you would like to make, and there's a nice video here, and you can program by changing this tubes here, some of these tubes and some of these vials, and you can make a variety of different molecules, which will be chemical synthesis, a 3D printer for chemical synthesis. Here's another example of what they called futuristic chemistry. You can print billions of possible compounds by just reconnecting things, and it's been described in the literature. There's various applications to medicine. This is from the Journal of Science. It shows 3D print on demand for bone to recover from, to mend major injuries. And here I don't have the time to get into it, but there is a nice guide to the future of medicine, at least according to the author. One can print mass spectrometers now, 3D print them. and I'm going to make the case for an ion trap. I'm not going to get into much detail, but all of this has been 3D printed. The pressure requirements are important for those in the know, but there's a lightweight for portability. As trap size is reduced, an ion trap is some of the traps ions, as the name implies, and the whole work is being pioneered by Graham Cooks of Purdue University. So, and it has all been published, and he will provide STL files to interested users. So you may want to contact him. One can print now molecules for teaching purposes instead of assembling them, and then you can have chemistry and crystallography together. Crystallographic example shown here. So you can reinforce learning through 3D printing. And again, another nice video is shown here. So you can print your molecules and bring them to class, depending on what molecule one is interested in teaching. So in conclusion then, 3D printing is a transformative technology, just as I mentioned in the introduction, and in my opinion, that will make an impact in science, technology, in medicine and healthcare, and overall, it will transform society by allowing everybody to print whatever it is special thing they would like to print. I will be happy to answer any questions you may have and facilitate discussion. Now, I'm not sure how this is going to work with this being narrated PowerPoint, but we'll try and see if there are any questions, and I may be able to answer. This slide was prepared for when the tutorial was supposed to take place with individuals present. Thank you very much for your attention and patience.